Hello and welcome back to the second segment of lesson 15. In the previous segment, I showed you how to organize data using counting, sorting, and grouping. In this segment, we're going to look at more analyzing data, specifically time series data using correlation, resampling, and smoothing. So I'm going to switch to the notebook now. Okay, so we have the notebook here as before. It's linked from Canvas modules, and we're going to be using the second data set in the data folder, washingtonweather.csv. What is this? Well, what I've done is downloaded some weather station data from Seattle and Spokane, some of the longest running weather stations in the region. From Seattle, it's from SeaTac Airport, and from Spokane, it's from Spokane Airport. This data has temperature, daily high-low temperature in Fahrenheit, and precipitation in inches per day from 1980 to present. So it's daily resolution. And this comes from NOAA's NCDC Climate Data Online website over here. Okay, so we've loaded the data and have the file path. Parse the date column as date times. And let's just say display Washington data. So what are we working with? Well, we have this Pandas data frame. You can see that it has under the name column, you see the SeaTac data is sort of stacked on top of the Spokane data. So we're going to need to kind of pull these out because we want to work with them separately. You can see that the index over here goes from 0 to almost 30,000, so it's a lot of entries. The dates start at 1980 and in 2020. Precip, Tmax, and Tmin. We're going to be working mostly with Tmax in this segment here. Okay, so let's divide that data out. I'm just going to say Seattle, variable Seattle is equal to Washington data.loc. So we're going to select certain rows. And in here, we're going to use a Boolean condition, say Washington data, column name, where that column is equal to, and let's copy over here, Seattle Tacoma Airport. So that full name over there. And then let's do the same thing for the Tacoma data. Or sorry, the Spokane data. Okay, Spokane International Airport. There we go. Okay, so we have these two variables, Seattle, Spokane. And let's actually make this date column here the index instead of the sort of arbitrary row number, because we want to, it's useful to have dates as the index. You can do a lot more things in Pandas with that. So Seattle set index, this is a new function. You don't have to know it, but it's a good one to know. Using the date column, and we're going to say in place equals true. This is a common argument you see in a lot of functions saying modify the variable in place as opposed to creating a new variable. Spokane, let's do that with Spokane too, and then let's just say display Seattle to make sure that this worked. Cool. Okay, so now we have only Seattle data. Dates over here is our index. This is what we want. Okay, and I've gone here and made a plot of the high temperature data. Just a line plot of the Seattle data, of the Spokane data, again, breaking it up into index values and then the data values for Tmax. Seattle's in black, Spokane is in blue, and made the line width pretty small so that we can see all these variations. Because we're looking at like 4 decades of data here. So you can see that there's this clear seasonal cycle. The temperatures in Seattle and Spokane are pretty similar, but there are definitely differences that you can make out if you kind of squint. And then there are, some maybe a trend over time, but it's really hard to see from this, right? So let's use group by, what we learned in the first segment, to calculate some climatologies and annual averages. But first, I think a really important thing to know here is that when you have this index of date times in a Pandas series or data frame, that's called a date time index. It's actually an object type. And this type of object, it has a few useful attributes: .year, .month, .day, and .day of year. .year is pretty much what you might expect. So if you do Seattle.index, this gives you that date time index object. And then if you say .year, you get this index that starts at 1980, 1980, 1980, 1980, et cetera, up to 2020. Right? So these are the years for each date time in the index. What about day of year? This is a really useful one here. Day of year starts at 1, it goes to 366 for the longest possible year, and you can see it starts 1, 2, 3, 4, 5, 6, etc., and it ends at 324 for this particular year for 2020 over here, because we're still in November, right? Okay, so these are two ways to get different properties from that daytime index, and we can actually use these to group by. So we're going to say group by the day of year, and that's called a climatology. So we're going to say Seattle.group by, and then we're going to just copy and paste this here, this day of year. So we're going to group over those day of years. So all the first days of the year are going to be grouped together. All the 180th days of each year, those are going to be grouped together also. And then over those grouped days of year, we're going to say dot mean. Okay, let's do the same thing for Spokane. And let's set these equal to some variables here. Let's say Seattle clim for climatology. You'll hear that word tossed around a lot, climatology. What is that? Well, if we display this, you can see it's this view of the date time of the data frame. The index now is date, or really it should be day of year. It starts at 1, it goes to 366. So this is the average maximum temperature, high temp, for every first day of the year, for every January 1st of each year from 1980 to 2020, et cetera. Might be more intuitive to view this in a plot. So I've plotted these climatologies for Seattle high temps and Spokane high temps. And if you look at this, it's this familiar curve, right? It's cold in the winter, it's warm in the summer. There are 365 or 366 days of each year. Black here is Seattle, which is a bit colder in the summer than Spokane, which is more of a arid climate. Although Spokane gets quite a bit colder in the winter because it's again, it's not by the ocean, it doesn't have that heat buffer. So this is a pretty typical climatology. There's some wiggling because it's we're looking at 40 years and there's some noisiness. So that's grouped by day of year. Let's do the same thing instead, grouping by year. What does that give us? Well, it gives us annual averages, and that's a really useful thing as well, right? Because it squishes all that annual variability into one single number for high temp for each year. And that lets us look at trends over multiple years. And we're going to call that Seattle and Spokane and let's just check out the result for Seattle. Here we go. Okay, so this is the average high temp over all days of the year in 1980 for Seattle, et cetera, for each year as we go down here. Okay, and then I've made it a plot here. Same thing, high temp, .index.values for the years, and then for the actual data, just .values. Okay, so these are our annual averages, and it's sort of this blocky variability here, but you can definitely see there are some years that are warmer. The years that are warmer in Seattle tend to be warmer in Spokane as well, and vice versa for cooler years. But there are some differences. For instance, over here, Spokane got really warm. Seattle was not so warm in whatever this year was. And you can kind of make out an upwards trend, right? We could use lin regress, NumPy or SciPy's lin regress, which we saw in the previous lesson to get that trend if we wanted. But instead, let's actually calculate some correlations between these two time series, these annual averages that we got by using group by. Okay. And recall that a column of a Pandas data frame, a single column is a Pandas series. And when you correlate two things, you want to use series, right? So you're correlating two Pandas series, S1 and S2 here, just as an example. And the syntax you use is S1.core S2. And you probably saw this in an earlier assignment, but we're going to think about this in a bit more detail here. What you get is the standard Pearson correlation coefficient, also known as R. This is probably familiar from lesson 14, right, from lin regress. And again, just like with lin regress, more commonly we'll be using R squared. R squared represents the proportion of variance in one variable that's explained by the other variable. Again, here's some API documentation for the core function, if you want that. And we're going to correlate these two time series of high temperature in Seattle and Spokane. So let's say one time series, Seattle and the variable tmax, so specifying a single variable, a single column name gives us a series rather than a data frame. And we can then correlate that series with Spokane and tmax. And then let's just call this R, gives us the R variable. And we'll print it, but instead of printing R, let's say let's print r squared, right? The r squared value is r double asterisk per squared. And it's about 0.54, which is saying that about 54% of the variance in annual average temperatures in Spokane can be explained by annual average Seattle temperatures or vice versa, right? So there's clearly a pretty nice relationship. So I've done that over here. I've plotted that relationship by just having a scatter plot of the Seattle temperatures versus the Spokane temperatures, just single dots. And I've also calculated the linear regression. So this is harkening back to lesson 14. Same thing. If you're confused about this, check out that lesson again. And then I've used those slope and intercept values to print or to plot a straight red dashed line here, representing that linear regression. So what does that look like? Well, here are the scatter points, clear relationship, sort of one-to-one over here. And this dashed red line cuts straight through those points, saying that when it's warmer in Seattle, it's also warmer in Spokane. When it's colder in Seattle, it's also colder in Spokane. And of course, there's some variability, like that, 1 year that we saw over here, which doesn't really fit that relationship, but generally that relationship holds. And 54% of the variance in Spokane is explained by temperatures in Seattle. Okay, so that's correlation. How about another really useful function, resampling? Well, we can downsample the time resolution of a Pandas series or data frame as long as it has date times as its index. We use the function resample. It takes a single argument, which is a frequency alias or offset alias. And if we go into this little guide over here, you can see all the different offset aliases that are available. I've copied and pasted a few common options here. H for hourly frequency, D for daily, W for weekly, MS for monthly start, in other words, monthly frequency, and then it assigns the start of the month as the resulting date. And then YS for yearly start, same idea there. And resample is similar to group by in that it gives you a view of the data that's not really useful. You have to apply a function to that view. So we might apply mean, max, or sum to get the average of that resampled data. So let's just do the exact same thing we did before, calculate those annual averages, except using resampling instead of group by. So say the Seattle Tmax column, and we're going to resample our frequency alias or offset alias. Let's use YS for year start, so annual averages, and let's say dot mean. So without the dot mean, this wouldn't be terribly useful, but we add the dot mean. And that's sort of the apply combine part of the split apply combine paradigm. What does this give us? Well, this looks pretty familiar, right? That's exactly what we saw before, except done differently this time. So resample is nice. It does something similar to group by, but for time series data, it's more powerful, and you might end up using this in different ways. Last thing here, let's look at some rolling averages. And rolling is very similar to group by and resample, but it returns a view of the data that sort of rolls over the data, shifting by one increment, one row each time. So sort of these overlapping views of the data. And that allows us to calculate running averages, also known as rolling averages, running means, and moving averages. So this works by calling the rolling function. There are a few arguments you want to be aware of. First is window. You have to say the size of that moving window that's going to look at the data in moving chunks. You might also want to specify the minimum number of periods to return data, minimum number of rows with valid data that you need to return data. Otherwise, it's going to give you an np.nan result. This becomes important at the start and the end of the data, because then your moving average is sort of sticking out over the end of the data, and it might not have enough data to be meaningful. And then center. This argument usually should be true, which means that the resulting date will be set to the center of each rolling window. If false, it will be set to the end of each window. So again, rolling behaves similar to group by and resample, in that it gives you a view that isn't really useful until you apply a function like mean or median to get the rolling mean or rolling median. So I've done that here. I'm not going to type out this code, but we have our Pandas series, the one column from the data frame, dot rolling, and we're going to calculate a 5-year running mean of this annual average temperature data. I'm going to try to smooth that out a little, smooth those wiggles. And we're going to say center equals true. And then we call that mean to get the rolling mean. We could also say median, right? And that would be the rolling median, which is also kind of useful. And we've done that for Seattle, Spokane. And I have these plots, same as before, but now I'm going to superimpose over here those 5-year running means. What does that look like? Well, here we go. Here's that in the fine line, the more transparent line, that more variable data that we saw before. And then in this solid, thicker line here, this is the smoothed version using rolling. And it's a 5-year running mean. You can see that it filters out a lot of that higher frequency variability. And here it's more clear that there's probably an increasing trend. It starts a lot lower than it ends up. These recent years have been quite a bit warmer than these earlier years on a rolling average basis. Okay, and same deal, except here for the climatology, which again was that sort of really wiggly seasonal cycle. And I'm going to use a 30-day running mean. So again, this window is just talking about how many rows is going to aggregate. Whatever unit the rows are in this case days, is going to be the units of this rolling mean. Again, center true. And here I'm saying min periods equals 1. So on the start and the end of that data, you can see at the end here, kind of something gets a little funky, right? So we need to, I would like that to go to the very end. So I'm going to say you only need 1 row of valid data for it to return a result. So here's our seasonal cycles. Same thing as before. You can see the wiggly data in the thinner line, and then in the more solid line here, we have those smooth seasonal cycles, which is more what you'd expect from a nice looking visualization. So this is just a way to analyze data. We've looked at a number of things in this segment: correlating, resampling, and smoothing data. And in the previous one, we saw how to organize it using group by, how to count it, and how to sort it. So these are just ways to work with Pandas data frames and series. And we'll explore some more of these in class on Tuesday. Let us know if you have any questions. Check out the documentation too, which is linked for each of these different functions, and hopefully see you in class on Tuesday.